Hello everyone, first of all thanks for being here in my YouTube channel. Please subscribe our channel for more number of electrical videos. Let's move on to the topic, that is relationship between line voltage, line current, phase voltage, phase current of star connected load as well as delta connected load. So definitely it's a derivation. Before getting into the derivation, I'll be discussing some basic general concepts of star and delta. So balanced star, so definitely these impedances are equal, and then phase angle also same, 120, 120, 120, both star and delta. That's why it is called as a balanced star and balanced delta. So next there is a star connection. So all the finishing end of the winding is connected to common points. Here common point will be there. So that's why it's called as a star. And then delta, end to end connection. This end is connected to here, starting end of another winding. See, finishing end of one winding is connected to starting end of another winding. So similarly, it's a delta in shape. So that's why it's called the delta connected one. Where we can find the application of these experiments or derivations. So these derivations we can find in star derivation. So we can find in transmission as well as distribution purpose. This one is for only transmission purpose, from the power plant to substations. This one is for power plant to substation as well as substation to your home. So if you connect R and one neutral, you will get a single phase 230 volts 50 hertz supply. If you want RYB on the neutral you connect, you will get a 3 phase 440 volt 50 hertz supply for your induction motor, lifting of water. There we are using 3 phase induction motor, right? So let's see the explanation for this diagram. See, there is a line current. So this is a line current. Current passes through any line, that is IR and then IY and then IB, right? So these are the line currents. So definitions, they'll ask what is line current, what is phase current. So next there is a phase current. So current passes through any branch. This current is flowing, right? This current is flowing into this branch. This current is flowing through this branch. So I phase is equal to IR is equal to IY is equal to IB. See here, both currents are same. Line current as well as phase current are same for this equation. From this equation, IR IY IB is equal to IR IY IB. So IL is equal to IFH. We can write one relationship directly. We will get it. See here, next for delta. So current passes through any line. IR, IY, IB are the line currents. See here, line current. This IB and this IY, IR are the line currents. So next is the phase current. Phase current, here it will be, line current will be dividing, right? So current passes through any branch. Here this is a branch. So current passes through any branch, that is IRB, R to B, right? This is R, this is B, this is Y. So current passes through this branch, IYB. Current passes through this branch, IRY. So I phase is equal to what? IRY, IYB, IRB. This is the equation. Next there is a voltage. We'll go through voltage. So what about line voltage? Voltage between any two lines, right? This is VRY, this VYB, and then this VRB. These are the line voltages. See here, VL is equal to, line voltage is equal to VRY, VYB, VRB. And phase voltages. So voltage across any branch. See, voltage across any branch, we are neutral, and then here we are VB neutral, and then here there is a VY neutral. Okay, VY neutral and then VB neutral. That is V phase. We are neutral. So our voltage between line to neutral, we can say phase voltage. Okay. We are neutral, VY neutral, VB neutral. That is the phase voltage. If you connect R1 neutral, you get phase voltage, right? So 230 volt, 50 hertz, will get it. So here from this one, there is a line voltage, across any two lines. That is VRY, VYB, VBR, right? Next there is a phase voltage. So phase voltage in the sense what? Voltage across any branch. See here, this voltage and then this voltage across any branches, VRB, right? And then next there is a VYB. So V phase is equal to VRY, VYB, VBR. So here we'll get VL is equal to V phase, but here we'll get IL is equal to I phase. In the star connection, current line current as well as phase current are same, and delta connection, line voltage is equal to phase voltage. Keep it in your mind. Next there is a derivation. Before getting into the derivation, we must know some basic definitions, right? So line current passes through any line, right? So and phase current, so current passes through any branch. See here, this branch and then this branch and then this branch, right? Next there is a, see here, see the equation, IL is equal to I phase, because same current is flowing through the branch also. So current will not be dividing. Same, IL is equal to I phase. Next there is a line voltage, between any two lines, VRY, VYB, VBR. Next there is a phase voltage, across any branch, or voltage between R to neutral, line to neutral. So V R neutral, R line to neutral, Y line to neutral, B line to neutral. So if suppose neglecting neutral, you will get VR, VY, VB. Without neutral also the star will work. Okay. So next is the derivation. So VRY, I can write VR minus VY, right? So apply loop equation. VRY is equal VRY minus VRN plus VYN is equal to 0. So definitely VRY is equal to VRN minus VYN, right? So this is the equation. Neglecting neutral, you get VR minus VY, right? So similarly, VY minus VB, and then VB minus VR, because voltage only we want to derive, because already IL is equal to I phase we got, right? So we want only voltage relationship now. So next we'll see. So we'll derive the equation of voltage. Already we got IL is equal to I phase. No need of again a derivation. Okay. So VL is equal to what? VRY is equal to VYB is equal to VBR. I'll take only RY, okay, VRY, because these two are equal. Similarly, we'll get answer. So VRY is equal to what? VR minus Vy, right? So I'll draw a vector diagram over here. There is a vector diagram. So this is VR, induced EMF in the R conductor. This is Y conductor, and then this is B conductor. So we want minus Vy and then VR. VR already will be there, and then minus Vy we want. So definitely this is minus Vy, right? And the phase angle is 120 degree apart each other. So this is 60 degree. Okay. So if you want VRY, I'll be taking one resultant over here, and you'll get VRY, right? So this one is VL, and this one is VR is what? V phase, right? This one is what? V phase. Already we have written the equation. V phase is equal to VR neutral is equal to Vy neutral is equal to Vb neutral is equal to, if you neglect the neutral, VR is equal to Vy is equal to Vb, right? So VR is the V phase. So I'll be using cosine rule now. VRY square is equal to VR square plus minus Vy square minus 2VR minus Vy cos 60. This is the cosine rule we can use. So VRY is what? VRY is equal to root of this VR square as it is, this Vy square minus 2 minus into minus plus, I'll take plus Vy cos 60, right? I'll substitute VR is equal to what? V phase, right? And then VRY is equal to what? VL. So VL is equal to V phase square plus V phase square plus 2 VR into Vy, that is V phase square, right? V phase into V phase square. So V phase square cos 60 is 1 by 2. 2 to get cancelled, you will get VL is equal to 3 times of V phase square. Finally, you will get VL is equal to root 3 V phase. This is the final equation of voltage. So current is IL is equal to I phase, voltage VL is equal to root 3 V phase. Similarly for VYB, if you want to know VYB is equal to Vy minus VB. So minus VB we want, so definitely you'll get here. So resultant you take here to here, substitute the this one, this is VYB, and then if you want VBR, VB minus VR, right? VB minus VR, definitely you will get minus VR over here. Only one is enough. So minus VR, just you take resultant over here, you will get like this VBR. So this is the vector diagram of your star connected load. For single phase power, power is equal to Vi cos phi. That is V phase I phase cos phi, right? For three phase, power is equal to 3 times of V phase I phase cos phi. This is in terms of phase voltage. Let me see in terms of line values. So power is equal to 3 V phase is equal to what? VL by root 3, right? So we got VL is equal to root 3 V phase. So V phase is equal to VL by root 3. So VL by root 3 into I phase is equal to IL. So cos phi. So definitely root 3 into root 3 is 3. VL IL by 3 is there, cos phi. So if this one get cancelled, only you get power is equal to root 3 VL IL cos phi. Okay, this is a derivation of this equation. Let's see another method for deriving the line voltage, line current, phase current of spark magnetic load. So similarly, there is a line voltage and then phase voltage, line current and then phase current will be there. Similarly, we apply VRY is equal to what? VR minus Vy, right? This is the diagram. So I'll be just trying one perpendicular line from OB, that is A, right? So this is 30 degree, total 60 degrees. One total is 120. Okay. So cos 30 is what? OC by OA, right? Adjacent by hypotenuse, right? So OC by OA. OC is what? This is total VRY by 2. And then this OA is only VR. So finally cos 30 is root 3 by 2. And then VRY is what? VRY is VL. So VL by 2. And then what about VR? VR is equal to what? VR is equal to V phase. So V phase. Finally we'll get VL is equal to root 3 V phase. This is a derivation. Next, there is a delta connected load. Here, delta connected load and then impedance are equal. That is a balanced. So the line voltage between any two lines, right? VRY, VYB, VBR, and a line current passes through any lane. These are the line currents. And then phase voltage across any branch. These are the phase voltages. And then next is a phase current. So current passes through any branch. That is phase current, right? So from this equation, we'll get VL is equal to V phase finally. So, but IL we need to determine, right? So, I can write KCL to the junction R. We will get IR entering, IBR also entering, plus IBR minus IRY is leaving. So, is equal to 0. Definitely, IR is equal to IRY minus IBR. We will get the equation, right? So, similarly, IY is equal to what here? So, IYB minus IRY, right? Similar equation. So similarly, IB is equal to, so this junction IB is equal to IBR minus IYB. You get the equation. So this equation we need for to determine the line current in terms of phase current. IR is equal to what? IRY minus IBR, right? So similarly, IR is equal to IY is equal to IB is equal to what? Line current. And then IRY is equal to IYB is equal to IBR is equal to phase current. So I'll be drawing one diagram over here. This is R conductor, this is Y conductor, this is B conductor. I'll just multiply current IR, IY, and then this is IB, right? So R is followed by Y, and then B is followed by R, and then Y is followed by B, right? So IRY is present over here. IRY will be there. Minus IBR we want. So opposite of this IBR. So definitely this one is minus IBR. So I'll be taking resultants here. So I'll just adding here to here. We will get IR. IR is equal to what? IL. IRY is equal to I phase from this equation. Okay. And minus IBR also equals to I phase. I'll be using cosine rule now. So IR is equal to root of IRY square plus minus IBR square minus 2IRY minus IBR minus IBR will be there. Cos how much this one? Total is 120. Half of this one 60 degree. This total, okay, 60. So cos 60. Okay. See here, IR is equal to what? IL. So IRY is what? I phase, right? I phase square, and IBR also is what? I phase square. So minus I phase square, minus square will get I phase square only. I phase square minus this minus into minus plus 2 IRY IBR. So definitely I phase square. IRY is I phase, IBR also I phase, 2 IR I phase square. So cos 60 is 1 by 2. 1 by 2, 2 get cancelled. You will get IL is equal to 3 times of I phase square. Finally, you will get IL is equal to root 3 I phase. This is the equation. Okay. Similarly, you can do for IY and then IB. Just you draw a diagram, you get answer. Even though some different notations, sometimes you get IR is equal to IBR minus IRY. Sometimes, okay. That time you have to take this negative opposite, right? So finally, for single phase power, power is equal to VI cos phi, right? V phase, I phase cos phi. For three phase power, power is equal to 3 V phase, I phase cos phi. So just substitute V phase is equal to what? In terms of line voltage, VL, and I phase is equal to what? IL by root 3. I phase is equal to what? Here IL is equal to root 3 I phase, and I phase is equal to IL by root 3. So cos phi. So this 3 can write root 3 into root 3, VL into IL by root 3 cos phi. So get this 3, this cancel, you get power is equal to root 3 VL IL cos phi. This is the equation, final equation of delta. Next, there is another one method to determine line voltage, line current, phase current of delta connected node. There is a line voltage VL and then line current IL. These are the equations. I mean phase voltage and then phase currents, right? So I will be applying KCL to the node R. So IR is equal to, see here, this node, IR is equal to IRY minus IBR. You will get it, right? So you draw the vector diagram for this one. So vector diagram is like this, right? Draw one perpendicular line from, I'll just mention the OBA or OAB, one point, midpoint I have taken. So I have drawn on perpendicular line. So you'll get one triangle, right? So cos 30 is what? Adjacent by hypotenuse, right? Adjacent is OC by OA, right? So OC is what? This is total is IR divided by 2, that is IR by 2. And then IRY, this is this part, IRY, OA part. So we'll get cos 30 is root 3 by 2 and then IL by 2 and then I phase. Definitely we'll get IL is equal to root 3 I phase. This is the equation. Okay. So till here you'll be right.